Night over Germany. A Lancaster bomber flies so low the crew can see ripples in the reservoir below. The pilot holds steady at about 60 feet. Too high and the weapon will skip wrong. Too low and the aircraft will strike the water. Airspeed hovers near 230 miles per hour. Ahead stands a wall of concrete built to power factories, cool steel mills, and regulate the flow of an entire industrial region. This is not area bombing. There is no wide target, no margin for error. This is physics at treetop height, and if it works, a single explosion could unleash a man-made flood across the Ruhr. By early 1943, the air war over Europe had entered a grinding phase. The Royal Air Force was striking German cities and industrial regions at night. The goal was to weaken production and stretch resources. But night bombing had limits. Crews navigated by dead reckoning, radio aids, and moonlight. Bombs often landed wide of specific factories. Entire districts might burn, yet a critical facility could survive. British planners began asking a sharper question. Instead of dropping tons of explosives across the city, what if one carefully placed strike could cause broader disruption? In western Germany, the Ruhr region stood at the center of the problem. It was dense with steelworks, coal mines, rail yards, and heavy manufacturing. It depended on water for more than drinking. Water powered turbines. It cooled industrial machinery. It fed canals that moved raw materials between plants. Interrupting that supply, even briefly, could ripple across production. Several major dams controlled that system. The Möhne Dam held back a vast reservoir feeding both hydroelectric stations and industrial water systems. The Eder Dam regulated flow into rivers connected to the Wasser Basin. The Sorpe Dam, built differently from the others, helped manage supply within the broader network. On a map, they looked like static structures. In practice, they were control valves for a region that produced weapons, vehicles, and steel in enormous volume. Destroying a dam is not like destroying a warehouse. A warehouse can burn and be rebuilt on its footprint. A breached dam releases stored energy all at once. The flood itself becomes the weapon. Downstream bridges can be swept away. Rail lines can be undermined. Electrical factories can be drowned. Factories built along rivers for access to water can suddenly find that same water rising through their floors. But there was a problem. The dams were not easy targets. The Möhne and Eder were massive concrete gravity dams. Their thickness at the base measured in tens of meters. Dropping conventional bombs onto the crest would likely scar the structure, but not break it. To truly breach such a wall, an explosion had to occur directly against the face of the dam, preferably underwater. Water pressure would then force the blast energy into the structure rather than venting it harmlessly into the air. German defenses made that approach difficult. Torpedo nets were strung across the reservoirs to stop underwater weapons from reaching the wall. Anti-aircraft guns protected the area. Approaching at normal bombing altitude reduced accuracy. Approaching low exposed aircraft to small arms fire, power lines, and terrain. A standard torpedo would be caught in the nets. A standard bomb dropped from high altitude would not hit precisely enough. A heavy bomb dropped from low altitude might skip or detonate incorrectly. The target required a weapon that could bypass the nets, strike the wall, sink along it, and explode at a set depth. That combination did not exist in early 1943. At the same time, British leadership was under pressure to demonstrate that Bomber Command could strike with purpose, not just mass. Precision was becoming a strategic goal, even if technology lagged behind the ambition. The dams represented a chance to combine engineering with targeting. If they could be breached, the result would be visible and immediate. Water does not hide damage. A broken dam announces itself. Yet planners understood the risk. A mission like this would demand extremely low-level flying at night over defended territory with no room for navigation error. It would require exact speed and altitude control. It would demand crews trained for one specific task, not a general bombing run. In other words, this would not be another sortie added to the calendar. It would be a purpose-built operation, designed around a single technical idea. The question was whether someone could design a weapon capable of doing what ordinary bombs could not. The answer would come from an engineer who believed that sometimes the solution to a massive wall of concrete was not more explosive power, but a different way of delivering it. The idea did not begin in the cockpit. It began at a drafting table. Barnes Wallis was an engineer by training and instinct. Before the war, he had worked on airships and aircraft structures, studying how weight, stress, and pressure moved through metal frames. He believed that understanding force was more important than simply adding more of it. When planners looked at a dam and saw a wall too thick to break, Wallis saw a structure that responded differently depending on where and how it was struck. Concrete is strong when pressure spreads evenly across it. It is far less resilient when a shock wave is forced directly into its base. An explosion underwater behaves differently from one in air. Water does not compress easily. When a charge detonates below the surface, the pressure wave travels efficiently and pushes hard against anything nearby. If that blast occurs tight against a dam wall, the energy does not dissipate upward, it drives inward. That was the principle. The challenge was getting a large explosive charge into exactly the right position. German defenses around key reservoirs included anti-torpedo nets stretched across the water. A standard torpedo would be caught before reaching the wall. A conventional bomb dropped from high altitude must land somewhere in the reservoir, but not precisely enough. Even a bomb dropped from low level would likely sink before reaching the target face. To breach a gravity dam, the explosion needed to occur directly against the structure and at depth. Wallis searched for a way around the nets. He drew on a simple observation. A flat stone thrown across water can skip. If it's given backspin, it behaves in a controlled way, bouncing across the surface before losing energy. The spin stabilizes the path. Wallis believed that the same principle could be scaled up. His proposal was unusual. Instead of a bomb that fell straight down, he envisioned a cylindrical weapon spun backward before release. Dropped from low altitude at the correct speed, it would strike the surface, skip across the water, pass over the torpedo nets, and impact the dam wall. The backspin would cause it to hug the face of the dam as it sank. A hydrostatic fuse would then trigger detonation at roughly 30 feet below the surface, where the water pressure would amplify the force against the concrete. The concept demanded precision. Altitude had to be around 60 feet. Airspeed had to be near 230 miles per hour. Release distance had to be exact. Too high and the bomb would shatter on impact. Too low and the aircraft risks striking the water. Too slow and the weapon would not clear the nets. Too fast and it would overshoot. Early testing began with scale models. Small objects were spun and dropped to observe how they behaved on water. Engineers adjusted spin rate, shape, and weight. The mathematics had to match real-world behavior. Eventually, full-scale trials confirmed that the skipping motion could be controlled. The weapon that emerged from this process was called upkeep. It was cylindrical, not spherical. The total weight exceeded 9,000 pounds, including approximately 6,600 pounds of Torpex explosive. Torpex was more powerful than standard TNT and produced a stronger underwater shock effect. To function properly, the bomb had to be spun backward before release. An electric motor mounted in the aircraft would bring it up to the required rotational speed. Delivering upkeep required modifying the aircraft. The RAF Lancaster's bomb bay doors were removed. A special mounting frame held the cylindrical weapon externally. Crews would have to manage speed, altitude, spin, and release timing in one continuous run. There would be no second chance if the first approach failed. Within the Air Ministry and RAF leadership, the idea met resistance. It was expensive, it was specialized, it could only be used against certain types of targets. Training crews for a single mission carried risk. If the operation failed, the loss of aircraft and men would be significant, and the weapon would have little other purpose. But the proposal addressed a real strategic question. Area bombing was damaging, but it lacked precision. The dams were critical infrastructure. If breached, they would release stored water in destructive volume. The flood itself would become a weapon, damaging bridges, power systems, and factories downstream. By early 1943, the concept had moved beyond theory. Upkeep had been built and tested. The physics worked. The detonation depth was set. The spin system functioned. The calculations had been refined. What remained was not an engineering problem. It was an operational one. The weapon demanded flying at treetop height, at night, over defended territory. It required exact speed control and careful distance measurement. There were no modern laser rangefinders or precision navigation systems. Everything would depend on visual alignment and crew coordination. In effect, Wallis had created a precision strike tool before the age of guided munitions. It now required a unit capable of using it under combat conditions. The next step would not be refining the bomb. It would be building a squadron around it. Designing the weapon was only half the challenge. Delivering it would require something the Royal Air Force did not yet have, a unit trained for one highly specific task. In March 1943, a new squadron was formed for that purpose. It would be known as No. 617 Squadron RAF. The squadron was assembled at RAF Scampton, a bomber station already active in the air war over Europe. Crews were drawn from existing Lancaster units. They were not inexperienced airmen. Many had already flown operational sorties. What they lacked was training for extreme low-level precision at night. Command of the new unit went to Guy Gibson. Gibson was 24 years old, but he was already a veteran of numerous missions. He had flown both night fighters and bombers. He understood discipline in the cockpit. He also understood morale. The men selected for this operation would need both confidence and trust in one another. The margin for error would be narrow. From the beginning, the training made clear that this was not a normal bombing campaign. Crews practiced flying at about 60 feet above ground in water. That altitude was not chosen for drama. It was dictated by physics. The upkeep weapon would only skip properly if released at the correct height. Too high and the impact with the water would break it apart. Too low and the aircraft risked striking the surface. Flying that low at night introduced constant danger. Trees, telephone wires, and power lines were not always visible. Wind gusts could push an aircraft off level. A slight downward drift could end in disaster. Pilots had to learn to hold steady without climbing instinctively away from the ground. Speed discipline was equally strict. The aircraft had to maintain roughly 230 miles per hour during the attack run. Speed affected the distance the bomb would skip and the energy it retained before striking the dam wall. Even small deviations could ruin the attempt. Because modern precision instruments did not exist, improvised solutions were developed. To measure altitude over water, technicians installed two angled spotlights beneath the aircraft. When the beams converged into a single point on the surface, the plane was at approximately 60 feet. If the beams were separated, the aircraft was too high. If they overlapped too tightly, it was too low. It was simple, mechanical, and effective. Distance from the dam during the release also had to be exact. A basic triangular sight was mounted in the cockpit. When the towers of the dam aligned within the sight at a specific spacing, the bomb release point had been reached. There was no automation. The crew called out corrections in real time. The Avro Lancaster bombers assigned to the squadron were modified for the mission. The standard bomb bay doors were removed to accommodate the large cylindrical weapon. A special mounting frame was installed beneath the fuselage. An electric motor spun the bomb backward before release, bringing it up to the required rotational speed. All of this added complexity to aircraft that were already large and demanding to fly. Training accidents were a constant risk. Low-level flight left little room for recovery. Crews had to build muscle memory quickly. They practiced over reservoirs in Britain, rehearsing the approach again and again. Each pilot needed to feel what 60 feet looked like at night. Each navigator had to judge timing with precision. As the weeks passed, the squadron's purpose became clear to its members, even if the exact target was not always discussed openly. They understood they were preparing for a single, focused strike. This was not an ongoing campaign. It was one mission that had to succeed or fail in a matter of minutes. The secrecy surrounding the operation added pressure. The weapon was unusual. The tactics were unconventional. If word leaked, German defenses could be adjusted. The element of surprise was essential. By May 1943, the squadron was ready. 19 Lancasters were assigned to the operation. Crews were briefed on their targets and routes. They would cross the North Sea at low altitude to avoid radar detection, then penetrate inland toward heavily defended areas. The approach to the dams would be flown in darkness, with anti-aircraft fire expected once they were detected. Each aircraft carried not just a bomb, but a calculation. Altitude, speed, spin, and timing had to align. The entire mission depended on those factors coming together at the right moment. The engineering problem had been solved months earlier. Now it rested in the hands of young men flying heavy bombers at treetop height, preparing for a task that had never been attempted before in combat. On the evening of May 16, 1943, 19 Lancaster bombers lifted off from RAF Scampton. Their destination lay hundreds of miles away in western Germany. The mission carried an official name, Operation Chastise. The force totaled 133 aircrew. They did not climb into the high altitudes typical of night bombing operations. Instead, they descended soon after crossing the English coast. The route across the North Sea was flown at low level to reduce the chance of radar detection. Waves passed beneath the aircraft in darkness. Once over the Dutch coastline, the danger increased. Power lines, church spires, and anti-aircraft positions lay along the path inland. The formation was divided into separate waves, each assigned specific objectives. Navigation at low altitude demanded intense focus. Crews relied on map reading, timing, and visual landmarks. A single error could place an aircraft off course and into concentrated defenses. Even before reaching Germany's interior, losses began. Some aircraft struck obstacles while flying low. Others were hit by flak near coastal defenses. The mission was costly before the main targets were even in sight. The low-level approach that provided surprise also exposed the bombers to ground fire and terrain hazards. The first primary objective was the Möhne Dam. The reservoir appeared in darkness, its surface reflecting faint moonlight. The dam itself stood as a long, curved barrier of concrete. Anti-aircraft guns opened fire as the bombers began their attack runs. Tracers arced upward. The crews had trained for this moment, but training fields in England did not shoot back. Each aircraft approached alone. There was no mass drop. One plane lined up, held roughly 60 feet above the water, and accelerated toward the release speed. The two spotlights beneath the fuselage were switched on. When their beams converged on the surface, altitude was correct. The bomb spun beneath the aircraft. The triangular sight aligned with the dam towers. Release. The cylindrical weapon dropped, struck the water, and skipped forward in a controlled series of bounces. If the calculations were right, it would clear the torpedo nets and strike the wall. Several attempts were required. Aircraft made repeated runs through flak to achieve correct placement. Some bombs detonated without breaching the structure. Each run increased the risk. Crews could not vary much in altitude or speed without ruining the physics of the drop. Finally, one of the later releases struck and sank into position along the dam wall. Moments later, a deep underwater explosion forced pressure into the base of the concrete. A visible breach opened. Water began to pour through the gap, at first a narrow stream, then in widening torrents. The Möhne dam had been broken. With one major target breached, attention shifted to the Eder dam. The approach to Eder presented a different challenge. The dam lay within hilly terrain. There were no direct straight-line attack runs over open water. Pilots had to navigate around rising grounds before aligning with the target. Anti-aircraft defenses were lighter than at Möhne, but the geography made precision more difficult. Again, aircraft approached individually. Again, altitude and speed were held steady. The weapons skipped across the reservoir surface toward the wall. It took multiple attempts here as well. Adjustments were made in real time. Finally, an underwater detonation fractured the structure. A large section collapsed, and water surged through the opening into the valley below. Two primary concrete dams had been breached in a single night. The third objective, the Sorpe dam, was constructed differently. It was an earth-built dam with a concrete core, rather than a massive gravity wall. This altered how the weapon would affect it. The attack profile required a different approach, flying along the crest rather than perpendicular to the face. Upkeep bombs were released, and damage was inflicted. However, Sorpe did not experience the same catastrophic breach as Möhne and Eder. The structural differences limited the effect. It was damaged, but it held. By the time the surviving aircraft turned for home, 8 Lancasters had failed to return. The mission had achieved its primary engineering goal. The bombs had skipped, struck, sunk, and detonated at depth. Concrete walls had fractured. Stored water had been released. But the cost had been heavy. As the remaining aircraft crossed back over the North Sea toward England, the scale of what had occurred was still becoming clear. Behind them, massive volumes of water were racing downstream through industrial valleys. Bridges were being torn apart. Buildings were being flooded. Rail lines were being undermined. The raid had lasted only a few hours. Its consequences would unfold over days. Operation Chastise had proved that a highly specialized unit, built for one precise objective, could strike at a structural foundation of an industrial system. It had also demonstrated how narrow the margin was between success and loss. The dams had not fallen to mass bombing. They had fallen to calculation, training, and a weapon designed to behave in a way no bomb had behaved before. When the walls gave way, the stored energy of 2 vast reservoirs was released in minutes. At the Möhne dam, water forced through the breach in growing volume. What began as a violent surge became a rolling wall of floodwater moving down the valley. The reservoir had been holding back millions of tons of water. Gravity did the rest. The same pattern followed at the Eder dam. The rupture widened. Entire sections of concrete had collapsed. The water below did not trickle outward. It accelerated. In the darkness of early morning, downstream communities had little warning. Bridges were among the first structures to fail. Many were built close to river level to allow traffic and rail movement. A sudden rise in water tore at supports and undermined foundations. Railway lines were twisted. Roads disappeared beneath debris. Power stations along the riverbanks were flooded. Industrial buildings that deepened on steady water flow now faced uncontrolled surge. The flood did not distinguish between military and civilian sites. It moved through villages, farms, and worker housing. Among those caught in its path were German civilians and large numbers of forced laborers brought into the Ruhr to support wartime production. Casualty figures vary across sources, and precise totals are difficult to confirm with absolute certainty, but the human cost was substantial. Factories relying on controlled water intake were forced to halt operations. Electrical generation tied to the dam's hydroelectric systems was interrupted. Canals that linked industrial sites were affected as water levels fluctuated unpredictably. In the short term, disruption was real and visible. Rail transport slowed as bridges were assessed or rebuilt. Water supplies to certain plants had to be stabilized. Cleanup crews worked along riverbanks, clearing debris and repairing damaged infrastructure. Industrial managers had to account for flooded workshops and damaged machinery. The psychological impact was immediate. A structure believed secure had been breached from the air. The idea that dams deep inside Germany could be attacked successfully forced a reassessment of vulnerability. But the longer-term picture was more complex. German authorities mobilized rapidly. Repair crews were organized almost at once. Forced labor was heavily used in reconstruction. Temporary measures were put into place to stabilize remaining dam structures. Engineers began sealing breaches and reinforcing weakened sections. At Möhne, efforts to close the gap moved quickly. By late summer 1943, significant repair work had already restored much of the dam's functionality. Eder followed a similar pattern. The speed of reconstruction surprised some observers in Britain who had hoped for longer-lasting paralysis. Industrial output dipped in the immediate aftermath. Water levels required management. Power supply was adjusted. Yet the Ruhr's production network proved resilient. Alternate systems were activated. Damaged facilities were repaired or rerouted. The third target, the Sorpe Dam, though damaged, did not release catastrophic flooding. Its earth-filled construction absorbed the attack differently. As a result, its contribution to overall disruption was more limited than the breaches at Möhne and Eder. From the air, the results looked dramatic. Photographs showed massive gaps in concrete walls. Aerial reconnaissance confirmed wide flood zones and destroyed crossings. News of the success reached Britain quickly, though many details remained classified. Within Germany, authorities downplayed aspects of the damage publicly, while working urgently behind the scenes to restore capacity. Strategically, analysts began assessing impact in measured terms. The raid had demonstrated that key infrastructure could be targeted with precision. It had caused real, short-term disruption. It had destroyed transport links and flooded industrial areas. It had forced Germany to divert labor and resources toward repairs. At the same time, it had not permanently crippled the Ruhr. The flood itself became both symbol and statistic. For those in its path, it was immediate and destructive. For military planners, it was a case study. How much industrial slowdown had been achieved? How many resources had been diverted? Was the effect worth the cost in aircraft and trained crews? Those questions would shape how the raid was judged in later years. In the days following May 17, 1943, however, the visible fact remained clear. A flood had moved through the valleys of the Ruhr. The image of water pouring through broken walls carried weight far beyond the numbers on a production chart. Now the debate would turn into whether that weapon had changed the course of the war, or simply marked a dramatic chapter within it. German authorities diverted labor and engineering units to reconstruction. Those resources could not be used elsewhere while the damage was being addressed. But strategic effect is measured in duration, not shock. By the summer of 1943, major repair work at the breached dams was already well underway. Reconstruction was accelerated by extensive use of forced labor. Temporary structures were installed to regulate flow. Concrete gaps were sealed. Hydroelectric output was gradually restored. The German war economy, though stressed, adapted. Industrial production of the Ruhr did not collapse. Historians who have examined records of output and repair timelines generally agree on a balanced conclusion. The raid caused serious short-term disruption. It forced Germany to commit manpower and materials to recovery. It interrupted transport and energy supply. Yet it did not permanently cripple industrial capacity in the region. That does not mean the operation lacked value. Warfare is not only about destroying factories, it is also about forcing an opponent to respond. The need to repair dams required planning, materials, labor, and protection. Anti-aircraft defenses were strengthened around other critical infrastructure. Security measures increased. Strategic attention shifted toward protecting high-value targets that might previously have seemed safe. There was also the matter of morale. In Britain, the raid was received as proof that innovation could produce tangible results. The idea that a specially trained squadron, using a unique weapon, could strike deep inside Germany resonated strongly. News of the breach at the Möhne Dam was particularly dramatic. For air crews within Bomber Command, the mission demonstrated that precision could be achieved under extreme conditions. This was not a city engulfed in flame. It was a defined engineering target struck as planned. Within Germany, the psychological effect was different. The dams had been considered heavily protected. The idea that low-level night attack could bypass defenses challenged assumptions about safety deep within the Reich. It reinforced the message that no region was completely beyond reach. Still, measured analysis demands restraint. Operation Chastise did not stop steel production across Germany. It did not halt weapons manufacturing for months. It did not force a decisive strategic shift in the war's trajectory. The industrial network recovered. Replacement structures were completed. Water supply stabilized. The debate among historians is often centered on proportionality. 8 aircraft were lost. 53 trained aircrew were killed. The resources invested in developing the upkeep weapon were significant. Was the resulting disruption worth that cost? There is no single numerical answer. From a purely industrial perspective, the effect was temporary. From a military innovation perspective, the mission marked an important moment. The raid also influenced later thinking about strategic bombing. A well-designed operation could achieve dramatic results, but lasting impact required either repeated action or broader structural vulnerability. It was carried out in a time dominated by mass bombing campaigns, yet it pointed toward a model of targeted infrastructure attack that would become more common decades later. The combination of specialized weapons, trained crews, and clearly defined objectives represented a different approach from simply dropping larger tonnage. Success in this case depends on how it is defined. If success means permanent industrial collapse, the raid did not achieve that. If success means breaching heavily defended dams and forcing immediate disruption, it did. If success includes morale and demonstration of capability, the impact was significant. Operation Chastise became more than a single night's work. It became an example, studied, debated, and remembered as both a technical achievement and a reminder that even dramatic results must be measured against long-term outcomes. When the surviving Lancasters returned to England in the early hours of May 17, 1943, the scale of loss was already clear. 19 aircraft had taken off from RAF Scampton. 8 did not return. Of the 133 aircrew who began the mission, 53 were killed. 3 were captured. The rest landed with aircraft that were often damaged, fuel low, and crews exhausted from hours of low-level flying under fire. The numbers alone tell part of the story. Each Lancaster carried a crew of 7. Pilot, flight engineer, navigator, bomb aimer, wireless operator, and gunners. They trained together. They relied on one another. When a bomber failed to return, it meant an entire crew was lost or scattered. The average age of those airmen was young. Many were in their early 20s. Some were even younger. They had volunteered for a mission unlike any other, knowing the margin for error was narrow. Flying at 60 feet over enemy territory at night was dangerous even without anti-aircraft fire. Add flak, power lines, and repeated attack runs, and the risk multiplied. Several aircraft were lost before reaching the primary targets, brought down by defenses along the route. Others were shot down during the attack itself. A few struck obstacles while flying low. The mission demanded a flight profile that left little room for recovery if something went wrong. In the days that followed, families were notified. Loss lists were compiled. The squadron that had been formed for a single purpose now carried a permanent mark of that night. For leadership during the operation, Guy Gibson was awarded the Victoria Cross. The award was announced within days of the raid. It recognized not only his personal courage, but his role in coordinating repeated attack runs under fire at the Möhne Dam. Other members of the squadron received decorations as well. Distinguished Service Orders, Distinguished Flying Crosses, and other honors were awarded across the unit. The citations reflected specific actions, holding steady during heavy flak, completing runs despite damage, maintaining formation discipline under pressure. Awards, however, do not erase absence. Within the squadron, the cost was felt immediately. Empty chairs in briefings, missing voices in the mess, aircraft that would not return to the dispersal line. This unit had been assembled for a unique operation, and in completing it, it had absorbed heavy loss. Yet 617 Squadron did not disband after the raid. Instead, it evolved. The experience gained during Operation Chastise shaped its identity. The squadron developed a reputation for precision strikes and specialized missions. In later operations, it would be tasked with attacking hardened or high-value targets, including heavily defended ships and fortified installations. The mindset established during training for the dams, careful preparation, exact flying, technical coordination, became part of its operational character. For the wider public in Britain, the story of the Dambusters quickly moved beyond casualty lists. The dramatic breach of concrete walls captured attention. The narrative of innovation and daring overshadowed the cost for many observers. Newspapers reported success. Newsreels highlighted the damage inflicted. Within military circles, analysis continued. The raid would be studied for both its achievement and its losses. The destruction of 8 aircraft in a single night was significant. Trained bomber crews were not easily replaced. Each represented months of preparation and experience. The balance between risk and reward became part of the broader debate about strategic bombing. Operation Chastise demonstrated what precision could accomplish, but it also underscored how expensive such precision could be when executed under extreme conditions. For the men of 617 Squadron, the raid defined them. They had flown a mission that few others could have attempted. They had seen a weapon behave exactly as engineers predicted. They had witnessed massive concrete structures fail under calculated force. They had also watched aircraft disappear into darkness and flame. In the months and years that followed, the name Dambusters would become shorthand for innovation and daring. But behind that name stood 53 men who did not return from a mission built on precise mathematics and flown at the edge of possibility. The success was real. So was the price. The night of May 16th and 17th, 1943 ended in darkness over Germany, but the story did not stay there. Within weeks, Operation Chastise had moved from classified report to national narrative. Photographs of the breached Möhne Dam circulated through official channels. The image of water pouring through broken concrete became symbolic. It was visible proof that a carefully planned strike could produce dramatic results. In Britain, the raid was framed as a triumph of ingenuity. An engineer had solved a problem others considered impossible. A specially formed squadron had carried out a mission that required skill beyond routine bombing. The combination of science and courage made the story compelling. After the war, the memory of the operation was reinforced through film and literature. The 1955 motion picture, The Dambusters, helped fix the narrative in public consciousness. It presented the mission as both technical breakthrough and human drama. For many viewers, the film shaped how the raid was understood for decades. Popular memory tends to simplify. The dams were breached, the flood surged, the squadron became legendary. Yet historical assessment remained more measured. Scholars studying wartime production records noted that the industrial disruption, while significant in the short term, was not decisive. German repair efforts were rapid. The Ruhr's output recovered. From a strictly economic perspective, the raid did not permanently cripple war production. That dual reality, dramatic tactical success combined with limited long-term industrial effect, has defined much of the historical debate. But legacy is not measured only in output charts. Operation Chastise influenced how militaries thought about precision. It demonstrated that a highly specialized weapon, delivered under carefully controlled conditions, could strike infrastructure once considered beyond practical reach. The mission required integration between engineering, design, and operational execution. That model, designing a weapon for a specific structural weakness, would appear again in later conflicts. Barnes Wallis himself continued working on large, high-impact munitions. His later earthquake bomb designs followed a similar logic, used physics to magnify destructive effect rather than simply increasing explosive quantity. The idea that the method of delivery could matter as much as the explosive load gained traction. For No. 617 Squadron RAF, the legacy extended beyond a single operation. The squadron remained active throughout the war, taking on other demanding assignments. It participated in later precision strikes against hardened targets, including attacks on the German battleship Tirpitz. The reputation for accuracy and specialized capability became part of its identity. Culturally, the Dambusters story occupied a distinct place in British memory. It combined technical ingenuity, disciplined training, and visible results. Unlike many bombing operations where destruction was diffuse and impersonal, this raid had a clear before and after image: intact dam, broken dam. At the same time, modern reassessment has broadened the narrative. Historians have paid closer attention to the human consequences downstream, including the deaths of civilians and forced laborers. The moral complexity of strategic bombing has become more openly discussed in post-war scholarship. Operation Chastise, while precise in engineering terms, was still part of a wider air campaign that affected both military and civilian populations. The myth, therefore, is not entirely false. It is incomplete. The mission was bold. It required exceptional flying skill. It achieved its immediate objective. It also carried heavy cost and produced consequences that extended beyond factories and power stations. In military education, the raid is often studied as a case of problem solving under constraint. Limited tools, heavy defenses, and structural obstacles forced innovation. The result was a weapon and tactic tailored precisely to the target. That approach, designed around the vulnerability, has echoed through later decades of strategic planning. Technical advances have changed how precision is achieved. Modern guided munitions use electronics rather than spin and spotlights, yet the core principle remains familiar. identify a structural weakness, deliver force at the correct point, and let physics amplify the result. It was carried out during a time dominated by mass bombing, yet it hinted at a future where individual targets would matter more than tonnage totals. Memory has preserved the image of Lancasters flying low over dark water. History has added context about repair, recovery, and cost. Together, they form a more complete picture. The dams were rebuilt, the floodwaters receded, but the example set that night of engineering paired with disciplined execution remains part of the larger story of how air power evolved in the 20th century. Operation Chastise did not end the war. It did not bring German industry to a permanent halt. Production resumed, the Ruhr kept working. But for a few hours in May 1943, calculation overcame concrete. A weapon built on backspin and pressure did exactly what its designer predicted. A squadron trained for one narrow task carried it out under fire at treetop height in darkness. The breach in the dam walls proved that infrastructure once thought untouchable could be reached. The raid sits in that space between legend and ledger book. The numbers tell one story. What remains certain is this: the Dambusters showed that precision, when paired with preparation, could reshape how wars were fought, even if only for a night. I'm Dave. I appreciate you watching. Please subscribe, like, comment, and share. And until next time, stand tall.
He's a Dave, dude. Dave's got to stick together, you know what I mean?